Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everyone. I'm very happy to have this talk on the self-avoiding walk on the hexagonal lattice. I've met Hugo in several conferences earlier, and each time I'm doubly more impressed than the previous time, so I don't know how many times he can keep that up. And so, please, Hugo.
Thank you very much. So thank you for the invitation. So I will be talking about the self-avoiding walk today, and I have two main goals. My first one is to prove a conjecture on the connective constant of this model. So that will be the first part, and that's totally basic. So I really hope you will get the proof before the end. And the second part is trying to explain somehow this proof, because you will see that it can look a little bit black magic. So I want to explain, to motivate the introduction of the objects I will use. And to do that, I think it's better to see self-avoiding walk in a bigger frame. It's a part of a bigger family of models. So I will explain a little bit through these models how you can be led to this kind of proof. Okay, so to be sure that we agree on the model, you take the honeycomb, hexagonal lattice, and you take self-avoiding trajectories starting at some point A, say the origin. So it doesn't change anything to the model. I will start at mid-edges and end at mid-edges. Okay, and if I denote Cn the cardinality of the number of self-avoiding trajectories of length n, there is a natural question, which is to try to estimate this when n goes to infinity. So I guess you all know that this number grows exponentially fast. That's just due to submultiplicativity. If you take a n plus m self-avoiding walk, you cut it after n step, you get an n-step self-avoiding walk and an m-step self-avoiding walk. So globally, you have this inequality. And together with ad hoc estimates, saying that you grow like an exponential, you can deduce that Cn to the 1 over n converges. So in other words, Cn is some mu c to the n plus small tau of n. And this mu c, this connective constant, usually you don't expect it to have any nice value. But there is one special case where there were a prediction made by physicists. It's the case of the hexagonal lattice. So in 1982, Nienhuis conjectured that the value was square root of 2 plus square root of 2. And how it does this is kind of even more black magic than the proof I will present. And it used Coulomb gas formalism, and so a lot of deep physics behind this. But it's not rigorous. So this is the first rigorous proof of this thing. Okay. So the first thing we are going to do is not to work with self-avoiding walk. So we are simplifying the model by looking at self-avoiding bridges. So that's almost a walk, except that the first point is the lowest one, and the last point is the highest one. So this is called a bridge. And the nice property with bridges is that actually they grow exponentially fast and at the same speed as the self-avoiding walks. And it's easier to work with self-avoiding bridges. The reason is that they are used in the decomposition of self-avoiding walks. You should really compare this to, say, excursion of a random walk away from zero. That's easier to handle usually. Okay, so why is it true? Because a priori it's not obvious. So there is one bound which is straightforward, is the fact that there is less bridges than self-avoiding walks. And what you need to prove is the other bound. So how do you do that? So the first thing you can try to do is to take a self-avoiding walk and send it to some bridge. Try to see if you can associate naturally a walk to a bridge. So let's take a walk like this, and let's try to construct a self-avoiding bridge from that. So the idea is that you take the maximum of your walk and you just unfold your walk. You see, this part, I'm gonna reflect it above. And I can iterate the reasoning. I unfold and I carry on until I do the same thing below if I need to, and I will exactly get a self-avoiding bridge. So to any walk, I can associate a bridge. And the question is, to any bridge, did I associate a lot of walks or not? And in order to see that it's not that bad, what you can try to look at is a reverse procedure. And if you give me a walk and a partition of n, say, I can give you a bridge and a partition of n, I can give you a walk. Because the partition will exactly correspond to points where I fold back. So I start from here and you tell me after 2 steps you fold and so on. So what you know is that the number of walks is necessarily bounded by the number of bridges times the number of possible pre-images, which is the number of partition of n in the base case. So, of course, there are a lot of partitions that will not work, that will not send you back to a self-avoiding walk. But every self-avoiding walk will be every self-avoiding walk that is sent to this bridge, you can recover it for some partition.
So why is it partitions and not ordered partitions?
I mean ordered partition in this case. Ordered partition, sorry. I should have said that.
But then why isn't the number of them exponential?
Because here when you unfold, the steps are smaller and smaller necessarily. Because in the construction, you... So that's a very good question. So I will be putting some stuff under the ground every time. So if you see them, that's even better. Okay. So now what is remaining is to try to prove that there is not too many partitions. So either you know by heart what is the equivalent of this, and so you know very well Ramanujan and Littlewood, or you don't know it, and you just notice that the generating function of ordered partitions is this one. And this is of radius 1, exactly saying that Rn cannot grow exponentially fast. So you get... So what we are going to try to do now is to work only with bridges. Okay. So when you want to compute this kind of thing, usually you take the partition function, or the generating function, depends how you call it, and you try to find the radius of convergence. And usually you find this radius of convergence because you have, say, modifications that allow you to compute explicitly the partition function, because you have a functional relation that gives you exactly the partition function. So of course here you have no hope to have an explicit formula for the partition function of bridges. So the idea that we came with is that you can modify the partition function in order to get something where you can compute things. So before I present exactly the modification, I need a definition, very easy one. The winding of a curve gamma between 2 points A and B is just the number of turns you did in radian between A and B. So in the first case, for instance, here, you see that you did 1/4 turn on the left and 1/4 turn on the right. So basically, globally, you did 0/4 turn. So the winding is 0. But in this case, you did 4/4 turns on the left. So the winding is 2 pi. And so on. You could have other values, of course. So this is the winding of a curve. And now the parafermionic operator, so this modification of the generating function, it's almost the generating function. This would correspond exactly to the generating function, but I add a winding term here. So what does it mean, this thing? So I will be working with a special case of self-avoiding walk, which is the following. So I will be in this frame. So you take a finite domain, a simply connected one, but anyway, and one point on the boundary here, A. And actually, you will be working only with walks that are staying inside the domain. And so my function at point z, so mid-edge z, will be exactly the sum over all the walks starting at A and arriving at Z of the Boltzmann weight, so what should be involved in the partition function, but times this winding term. So if you arrive with a winding 0, you only count the Boltzmann weight, but if it's winding 2 pi, you will have a complex number in front of it. And I cannot emphasize too much that this is complex number. For many reasons. So sigma so far is nothing. I will explain after what it is. But that's a very good question. Now we know, but here we don't know. So that was a very good question. But sigma is real or not necessarily. It could be purely imaginary. There are cases where it's smart to look at it as an imaginary number. So let's say for now we don't know what it is. Okay, so we have the freedom in the choice of the sigma. And the idea is that if you plug sigma equals 5/8, and you will see why in the next slide, and if you plug mu equals square root of 2 plus square root of 2, then you get something non-trivial, which is this relation, this local relation. So what does it mean?
Could I just make sure I understand what everything is? So you're summing over walks or bridges?
Walks.
Walk. Okay.
Walks about.
Okay, and L of gamma is the length?
Exactly. Okay. Sorry. That's the length, yes.
Okay.
Really, that's the natural Boltzmann weight, the length. Okay, so what it means is that if you look at a vertex inside your domain, a vertex V, there is 3 mid-edges that are adjacent to this vertex. And what I mean is that some sum of the observable over these 3 edges equals 0. And the coefficient, if you are scaled by them, just think that it exactly corresponds, and that's something very important, to the discrete integral of the observable on this small contour equals 0. Sorry? So so it's just P minus V, that's this, and this. So there is nothing complicated in them. Okay?
They are vectors and the F's are numbers, complex numbers. So the F's
yeah. So that's an equality between complex numbers. Everything complex.
Well,
numbers.
Yeah. Vectors are... Okay.
I don't know numbers. That's complex numbers.
Okay. So it's R minus V as a complex number in play.
Yeah.
Okay.
And the F had 4 arguments, and now, okay, mu and sigma disappeared. What are...
Okay, so I don't want... So I can try to make the formula with that, but you will see they get bigger and bigger. So I will just forget about the initial point. I fix it for until the end, say. So the Z is a real variable, and mu and sigma here are fixed.
Okay.
So I will forget about the notations.
So A is some fixed starting point?
Yes. Really, you should think about that as a function in Z. Okay, so this exactly means the integral along this contour of F equals 0. The discrete integral. That's really what it means. Okay, so that's not the fancy formula. Okay, so where does it come from?
So you're trying to simplify the sum by writing it as a contour.
Yes, I'm hiding it. So okay. So I want to prove that this big sum equals 0. So this sum, when you think about it, it's a sum over all the walk that start at A and arrive either at R, P, or at P, Q, or R, of some weight depending on the curve, on the self-opening walk gamma, and which is equal to mu times minus the length. There is this winding number, whatever. And in front of it, if you arrive at P, you say P minus V. If you arrive at Q, that will be Q minus V, and so on. So I want to prove that the sum over all these self-avoiding walks equals 0, of this contribution equals 0. And the thing that I will manage to do that if I can make small groups of self-avoiding walks on which at each step, for each of these groups, I can prove that the sum of the contribution equals 0. So very, very simple arguments. And I will give you a first example. If you take a walk, say this one, that visits the 3 mid-edges around V, then you can naturally associate it to another walk that visits the 3 mid-edges. That's the same start, but you visit the loop that you do after in the other direction. You can always do that. So let's try to compute C of gamma 1 plus C of gamma 2. So this is C of gamma 1, so there is the 3 terms involved in the sum. Here also. And I see that there are many, many things that I can factorize actually here. They both have the same length. So the mu to the minus the length, I can factorize it. Q minus V and R minus V, I can express them in terms of P minus V. That's elementary. So I will factorize by P minus V, and I get 2 terms that are due to these expressions. And what is remaining is the winding term. And when I look at the winding between A and Q of gamma 1, it's the winding between A and P plus the winding between P and Q. The winding between A and P, that will be the same for gamma 1 and gamma 2 because that's the same start of the curve. So the only difference remains in the winding between P and Q is the winding between P and R for gamma 1 and gamma 2. But when I think about it, I know this winding. Why? Because I start on the boundary of my domain. So kinetically, the only thing I can do is this. I cannot do that. That's forbidden. So what I do, it's basically 1 turn on my right and 5 turns on my left. Perhaps I will do 2 turns on my right, but in this case I will make 6 turns on my left. The winding will be always minus 4 pi over 3, or 4 pi over 3, depending on which of these 2 curves you consider. But now if I put sigma equals 5 over 8, I get 0. This plus this equals 0. Trust me, you don't need to make the computation. Okay. That's the reason why we choose 5 over 8. And I will go further. I will explain more in more detail in the second part. You can do the same thing with walks that visit one site or 2 sites. You will factorize something and you will get this quantity, this ugly quantity. But if you put mu equals square root of 2 plus square root of 2, you obtain 0. So sigma, I chose it to make all the pairs vanish, and mu for the triplets.
So mu, there must be some trigonometric thing about mu, right? Is it
yes, that's a cosine of, so that's 1 over the cosine of, no, that's cosine of pi over 8.
Now that's
yeah, you see. I mean, that was obvious when you look at the model.
And somehow you have to, in this last one, you have to combine the ones visiting one site with the ones visiting
2 sites, because the natural thing to do is just to prolong. You have 2 ways of prolonging a walk, and if you start from one with 2 sites, you can just remove the last site and visit only 1 site. So all the walks that finish at P, Q, or R, I can put them into one of these groups. So my big sum equals 0.
So it's strange because you might imagine that under some circumstances there would be far more that just met at one site than any of that, but is that just not true?
No, that's not true. Because if you visit only one site, you can prolong it in two ways to get two sites. And if you visit two sites and not three, you can always remove your last step.
The big sum is all the walks that end where?
P, Q, or R.
Only a P. Oh, okay.
Yeah, because so this is the walk, that's the sum over all the walks that end at P. This one are all the walks that arrive at Q and R. Good question. No, but I mean, it means that it was not explained clearly enough. Apologize. Okay, so we are happy. So we know that the integral of f on this discrete elementary contour equals 0. So I know now, it's elementary, that the integral over all closed contour equals 0. So the end of the proof will be, can we choose the right contour and the right domain to get something that allow me to count things on self-avoiding walks. And it appears that this domain is a nice one, because that's, you try to minimize the number of computations. And this is the contour I will consider. And you will see just after why I consider this. So saying that the integral on this contour equals 0 is exactly saying that. Nothing more. Here I replace the P minus V and Q minus V by what it's equal to. So alpha, beta, and gamma are just the parts of the boundary I'm considering. Just beta is the top, alpha is the bottom, and epsilon and epsilon bar are the boundaries. So why did I take something on the boundary? Because on the boundary I know the winding. So remember that we are working with f. So okay, we have a nice formula for f, or I mean relations for f. But still, there is this winding term which is not positive, which is a complex number, and it can make a lot of cancellation, and you don't get anything on your model. So you really need to get rid of this winding term. And the way you do that is by considering something on the boundary. Because on the boundary, if you look at walks that arrive at beta, the winding of these walks, you know it. It's 0. You cannot wind around the boundary.
You're starting from the inside.
Yes. You start from here, and if you wind around it, it means that you get out of your domain. So you can express same thing for alpha, epsilon, and epsilon bar. You can get what is the winding in this case, and so you get a relation that only involves Boltzmann weights now.
Is this the reason you need the bridge, so that you won't have a winding on it?
Exactly. Why do you need a bridge? Because the bridge is typically something that goes from one side of a domain to another boundary of the domain. A walk is something that ends in the middle, and in the middle you don't control anything. So that's exactly that. So I was going to say that. So you have nice formula, 1 equals the cosine. You have some terms that are now just the generating function, and here, for instance, if you let the width going to infinity, you let L goes to infinity, you are working in a strip now, and this term is exactly the generating function of the self-avoiding bridges of height, say, so if you work with a height t, of height t. So here I'm counting self-avoiding bridges of height t.
What's the angle?
So don't matter. It's really to minimize the computations. And actually you let L goes to infinity, so it even disappears, this term. You only get these two terms. This one disappears. So really what I want to emphasize is that here I have the generating function of bridges of height t. So for instance, for free, what I get is that the number, so the generating function of bridges of height t is smaller than 1, because this term is positive. So I will not do it, because I guess you can do it by yourself, but so now, for instance, you can deduce that mu delta is not smaller than mu c, because if it was smaller, there would be this mu delta times the minus the length it will not beat the entropy. There will be too much entropy, and this term here will explode exponentially fast. And it's not the case. It's smaller than 1. So you get one inequality making this reasoning rigorous, and the other one is a little bit tricky, but nothing completely crazy. So finally, you finish the proof just by using this combinatorial equality. So I'm always afraid not to have time to finish, so I will not finish the proof, but if you want after the talk, you can ask me and I will finish it. So if you want, by the way, the proof is not on arXiv yet, but it's on my internet site and the one of Stas. So you can go, the proof is completely written there.
Why is it not on
Because we are waiting to prove more. We hope at least to be able to do more. Okay. So what I did so far is I determined the connective constant. So I sketched, of course, I skipped some steps, but easy steps. And I did that by introducing this weird function, this parafermionic observable. We don't know exactly where it comes from, but it works. And the important thing on this discrete observable is that it's discrete holomorphic in some way. The integral over all the closed path equals 0. So here you see the first connection with conformal invariance. You have something holomorphic in the discrete level. Okay, so what I'm going to do now is that I'm going to try to explain to you what we can do, what we would like to do further. And just to avoid one annoying question I get every time I explain this kind of thing is what you should not do next. Okay, so perhaps I should have started by this, but it's a good place also. What are the real conjectures for the self-avoiding walk, the complete one? So the first one is that, so these conjectures are due to Nienhuis, and he was a guy who guesses this, but he also had a hard argument to show that the correction in front of this mu to the n was a polynomial correction. And with a very special value, gamma, which is 43/32. And this gamma is universal, in the sense that if you take self-avoiding walks on, say, the square lattice, obviously you don't have as many self-avoiding walks. You have much more self-avoiding walks in the square lattice. So the mu c, the connective constant, is not the same. But the correction in front of it is exactly the same. It's n to the gamma minus 1. So that's this kind of weird things you can get from conformal invariance. Just a geometric questions, because we are probabilists, and that's...
Maybe it's worth saying in a word why this sounds completely crazy if you don't...
Yes, so I will explain it just after. Yeah, I will explain it just after, yeah. And I will explain it for this one, because that's a one-sentence explanation. If you look at a geometric question, like what is the mean square displacement of your walk, you will also get something which is equivalent to a power or something, and it will be, the nu will be universal as well. So this conjecture, Nienhuis got them by looking at Coulomb-Gall's formalism, so continuum limit of fancy objects. And I guess it's hard for us at least to understand where it comes from.
The 3/4 was much older.
Yeah, the 3/4, but it was older, but it was only numerical.
No,
so
there was a heuristic by Flory. It's a crazy heuristic.
There is this thing, yes, but I mean, that's just saying I have two things that should balance each other, so I look exactly at the time where they have exactly the same power and gives me the right quantity. So that's true, they were, but it was really, really, really heuristic. I mean. Okay, But now I guess we have a much more precise intuition why it should be true, and that's due to this conjecture by Lawler, Schramm, and Werner that the scaling limit of the self-avoiding walks is SLE 8/3. So I guess here everybody knows about SLE, so I'm not going to give too many explanations, but I would like to say what is converging to the SLE 8/3. So you take a domain, your favorite domain, and 2 points A and B on the boundary, and you consider a hexagonal lattice of very small mesh size. And you look at all the self-avoiding paths that start at A and arrive at B. So there is a very natural measure to put on them. Is like always, you want to penalize by the energy, so you will put a measure where the probability of some curve gamma would be proportional to some mu2 minus the length of the gamma. Oh, sorry, you don't see. You want something like this. So you can see that if you take mu very, very large, too large, you will penalize a lot by the length. So basically your walks, they would like to be to go straight from A to B. So there will be fluctuation, but they will disappear at the limit. On the other hand, if you take mu very small, you don't penalize enough, and you get something which becomes space-filling, and you get something which is not an SLE 8/3 at the limit, or at least not a curve that is nice. I will explain to you what it is later. But if you take mu exactly equal to the critical value in some way, and this critical value is square root of 2 plus square root of 2, that's the connective constant, then you expect to have a scaling limit for this object. So when the mesh size goes to 0, you should have a random continuous curve, and this curve should be SLE 8/3. Okay? So just 2 words about SLE 8/3. That's a Loeffner chain, and it has a drift, so a driving function, sorry, which is square root of 8/3 times a standard Brownian motion. So that's the 2 only things that I want to explain on that, because it will be useful for the next point. So perhaps before I can explain to you where these things come from. So you can do the same thing for the square lattice. And the right mu will be the connective constant for the square lattice. Would you expect to have exactly the same scaling limit? And somehow, now you start to understand that what will be universal is exactly what you can compute via your scaling limit. And that's exactly the spirit of universality. This thing, so I don't remember which one is the easiest to explain. So this one, this nu here, it's related to Hausdorff dimension of the curve. So that's an example why this nu should be universal, because it's connected really directly to the SLE. And other things you can, you have to be smarter, but you can get the other exponents via SLE. So everything that is universal should be, you should see it at the scaling limit and vice versa, in the sense what you can compute at the scaling limit is universal. Yeah?
And one sense, if you just take 2 self-avoiding walks of length n, concatenate them and ask what is the chance that the concatenation is still self-avoiding, then the mu cancels and you see
exactly.
So that's one way to see why expect that to be.
That's completely true. Yes.
So this power law is assumed to be universal.
Yes.
Right, so if you think that's something global, you take
It's like the self-contained.
Right, so the mu
sections
That things that you can compute at the scaling limit. So for instance, in this case, for the quantity Yuval talked about, it will be, the limit will be exactly the exponent, the universal exponent for the SLE8 third. Okay. Okay, so what we want to do now. So of course what we would really like to do is to prove conformal invariance, to prove this convergence. So I'm not going to do that today, unfortunately, I would say, but I can explain to you what should be the strategy. If you want to prove something like this, usually you need two ingredients. So the first one is a precompactness argument. You have your discrete curves here. You let the mesh size go to 0. Can I extract some sub-sequence that are converging? And actually, so converging to a continuous curve, that would be the right thing. And even a little bit more than that, you should have something that makes you converge to a Lovener chain. So it's just think that it's slightly bigger. You are slightly more than just just continuous curve as a limit. You want a Lovener chain. So precompactness we'll say a strong one, which gives you a Lovener chain. So once you know that that's a Lovener chain, that's not necessarily a conformally invariant object. I'm just saying you want a Lovener chain at the limit. The second step is to say, okay, now what I just need to do is to compute the driving function of this Lovener chain and prove that that's a Brownian motion. And the technique that you can use here is the following. If you know martingales of your curve that you can compute, like really you know, I don't know, E squared is a martingale for my curve. What you can do is you write Ito's formula and you say the a priori drift, it actually equals 0. It vanishes since that's martingale. But hidden in this drift, there is your driving process somewhere. It's perhaps not very explicit, but it is involved in the driving process, in the drift term. So if you have enough martingales, say, you can hope to have enough information on your driving process to get that that's a Brownian motion. And that's exactly the technique. So usually what you manage to prove is something like your driving process is a martingale, and your driving process squared minus 8/3 of t is a martingale. And you use Levy's theorem to say, okay, it determines my process. Okay, so that will be the technique. So what you need is a martingale which you can compute. And usually, necessarily because you are working with a conformally invariant object, you will get a martingale that is conformally invariant. But a priori, you will not need that. And this conformally invariant martingale, that should be this parafermionic observable. This is a martingale, so it's a small computation. And it should converge to something holomorphic that you can compute, because we know the boundary conditions, and you know already that there is discrete integrals that vanishes. The discrete integral vanishes. Whoa. Okay? Sorry?
What is the difficulty?
Okay, so what is the difficulty? Everything. That's very simple. Precompactness, in this case, we don't know how to do. Because you don't have, so usually for statistical model, you use like an FKG, Russo-Semmelweis kind estimate, so crossing of rectangles. Here you don't have this kind of things, because that's strongly non-Markovian and it depends on the whole curve. You don't know anything. So this is already a big open question to have precompactness. Second question is, okay, let's prove that this observable properly rescaled converges. I don't know how to do that. Why? Because this discrete holomorphicity should not be compared in any mean with, so you don't have the same strong rigidity properties that you have when you work with continuous holomorphic functions. if you fix the boundary of a domain, so the value on the boundary of a domain for a holomorphic function, you determine your holomorphic function. Here it's not the case. When you count the number of information you have one unknown variable by edge. And how many relations do you get? One per vertex. So there is twice less relation for the vertice, for twice less relation than variables.
For percolation, like, doesn't that have the same problem?
No, because somehow it's a different problem because what they prove is something stronger than that. And in the case, in the case of percolation, you have even something which is even nicer is that you know precompactness of your curve, of the observable and everything, which is not the case here.
I was referring to the last part, having the discrete.
Yeah, but they have precompactness. If you give me precompactness, you say it converges to a continuum function, then I will say Morera theorem. I have integral over the contours that equals 0. I'm holomorphic.
So if you know 1, 2 follows?
Not obvious. So that's very, very good question again. No, but that's true. I mean, it's very rare I can talk about that, so that's good. So that's a very good question. No, because the winding term is something so ugly that precompactness of the curve doesn't even guarantee that this winding term behaves nicely. So that's another problem. So it makes a lot of problems. Okay, but what you can do, okay, let's try to prove something. So what you can try to do is to have a bound on the correction term. So actually you have one which is totally for free from subadditivity, submultiplicativity. You get that it's bigger than mu to the n. The number of self-avoiding walks is larger than square root of 2 plus square root of 2 to the n. And the other bound, you would like to have a polynomial bound. And the best one you have is exactly the one I described to you. It's exponential of square root of n. So that's far from being the truth. So a little bit like you want to have good estimates on mixing time, here you will have you want to have good estimates on the correction term. So polynomial bound will be good, very, very good. And here it's a work in progress and it's going well. So you can play with the geometry and using more involved combinatorial arguments, and it should be working. So you can still do a little bit more than just the connective constant. Okay, so let's try to explain where this parafermionic comes from. And in order to do that, I will need to consider a new model. So this new model is a model on loops on my lattice. So I have still a discrete domain, and I consider a model where you have loops like this. And the probability of a configuration is proportional to the number of x to the number of edges you use to make your loops times n to the number of loops. Okay? So that's just, for people who know random cluster models, that's very close to this kind of model. But you don't have the same constraints on the configuration. So that's a model which is a representation for the spin ON model, which is even more famous. So the spin model is just, you put here, it will be on the faces of your graph, you put a spin, which is an element of the n-dimensional sphere. So O of 1 is the Ising model. So let's, O of 1 is the Ising model. And O of 2, for people who know that, is the XY model. And so on. So exactly like the random cluster models are the geometric representation of Potts model, here you get geometric representation of ON spin models. So already there is a strong parallel between these two family of models. And so Nienhuis studied actually the model for every n between 0 and 2. and it obtains the following diagram. So there is a critical line below which, so when you take x smaller than this, you get a subcritical model, in the sense that there is a correlation length. You see very small loops, logarithmic loops. There is this line, which is exactly corresponding. You see that's a generalization of the formula I presented to you before. And here, that's critical. There is no correlation length. And there is a second phase, and for us it's not common to see that, but there is a second phase where you see again critical phase. But it's not the same critical phase, in the sense that the critical exponents and everything that is depending on your model are not the same. Okay? So O of 0 is the self-avoiding works. This line corresponds to the self-avoiding works. X is 1 over mu. And the line here is it's the Ising model. Okay. So for this model, now I can try to create the same observable, see if there is a common frame for everything. So let's start with the Ising model. So you look at O of 1. So you have your lattice like this, and I'm going to put an Ising model on these mid-edges, just because I like it. So there are plus or minuses. So when you look at the Ising model, there is a natural thing you want to compute on it, is the correlation between 2 points. So, I mean, I don't need motivation to introduce this. Okay? And when you look at the high temperature expansion of the Ising model, you get loops and strings, and this is exactly the O of 1 as I described it. That's exactly the loops and are exactly the loops of the high temperature expansion of the Ising model. And this case, this quantity, when I compute it in terms of the ON model, O1 model, is exactly the partition function of my model times the partition function of my model, but I add a string between x and y. I must have a trajectory between x and y. So let's say here I'm in a domain with a lot of loops, and here I'm in the same domain with a lot of loops, but I must have a string between x and y. Okay, so that's, very natural to do. Now, what physicists like to do, and I will not be able to tell you why, is to add what they call a disorder operator. And what does it do, this disorder operator? It just takes the 2 points x and y and say, okay, I take one trajectory between these points, and I switch the conductance on along all this trajectory. So I force the spins to be frustrated in some way. I change this. Here I had, I don't know, between these two I have j. Now I will have minus j. When you look at this and you try to see what it is equal to in the loop representation, you can still do the same thing that before. But the thing is that you need to add a term in front of every of your configuration, and it will be 1. So here, this was just a sum of x to on the configuration gamma of x of the number of edges times n to the number of loops. So here I will have also this. But in order already to count the thing with the disorder operator, I need to add a term, and this term will be equal to 1 if the curve that was here does an even number of turns around y, and minus 1 if it does an odd number of turns. So here I must add something which is 1 or minus 1 regarding to the number of turns I do my curve does before reaching x. And this, if you think about it, you can rewrite this. So these two things, you can rewrite this like this. If you do an even number of turns, you will have a winding which is multiple of 4 pi. So when you divide by 2, it gives you a multiply of 2 pi, which is 1. You get 1 when you put the exponential. If you do an even number, an odd number, you will get minus 1. So what I found finally is something that looks very close to what I considered before. There is this winding term which is naturally happening here. And I'm not taking a fancy quantity. And this 1/2, it's called the spin in the case of the Ising model. And if you want, you can replace for other models, you can look at the natural spin somehow. And exactly, you change the sigma. Here you just say, I will not take 1/2. I will take some sigma, and in terms of n, there is a natural value of the sigma, which is this one. And you can check that for 0, it exactly gives you 5/8. So, of course, perhaps the best motivation for the sigma is to say it works. Like when I do, for ON models, I can do the same combinatorial trick, and I will get the right thing by choosing this sigma. But where it comes from deeply is from the fact that in the Ising model, that's really a very natural quantity to look at, and that's a natural generalization. So this sigma is connected to the central charge and the spin of the model. So it's called a parafermion, by the way. 1/2 was a fermion. It was really the spin of the particles in the ferromagnetism Ising model. Here, of course, sigma not equal to a half integer. It doesn't give you a spin in the sense of physics. So it was why it's called a parafermion, because it plays exactly the same role. Yes.
Isn't n equals 0 the self-avoiding?
Yes.
But if you put sigma as 5/8 there.
Yeah, because 5/8 and 3/8 are the same spin, actually. Yeah, they play a symmetric role. So really, when you try to introduce the observable, it's more natural to get this one, but when you want to work with, it's more natural to get the other one. And the duality is obvious to have, and you will get an anti-holomorphic function if you look at this sigma. It's why we don't like it. We prefer to have a holomorphic function. I mean, discrete holomorphic. So it's where it comes from. And so with that, you can try to do the same thing as in the self-avoiding walk. You will have the same problem. F is discrete, so same problem, no. So first, F is discrete holomorphic, exactly as before, and so that's basically the same proof. But as before, the discrete holomorphicity does not determine your function. So you have the same problem. Yes?
There is to get a pair of discrete holomorphic functions that are conjugate.
Yes. So, no, but...
One on the graph and one on the dual graph.
Yeah, but actually they are... So, in the case of the random cluster model, which in some way it appears a little bit more natural, you have a function which is directly defined on the medial graph. So, somehow in the primal and the dual graph already, and it's not sufficient either. So there is something sad about that. But there is a missing information, and if anybody has an idea where to look for it, so it'll be good. But somehow you have already the holomorphicity which is behind, because you have already this discrete holomorphicity. Okay, so the conjecture, just to finish. So there is this diagram. The conjecture is that on this line, when you look at the curve here, so let's say that you put this point here and this point here on the boundary, this curve should converge to an SLE with a certain kappa that you can compute. Okay? So that's not a conjecture for n equal 1, because here you have enough information. The spin 1/2, it's a very nice spin when you think about it, because you know the argument of your function in this case. So somehow you have twice more variables, but they are real variables, not complex variables, because you know the argument. And so in this case, you have enough information, and you can start to work really hard on that. And if you are very smart, you get that this observable converges and everything works fine. So you get convergence. Sorry?
You get the pre-compactness.
Yes, and you get it for free. You get it from, so not for free, but from the fact that, no, I mean for free. Oops, erase everything. You get it from the discrete holomorphicity, which is a very interesting fact, and which is, very natural as well. When you look at harmonic functions, say, they have naturally a smoothness which is very strong. You have very strong rigidity theorem for harmonic functions. And in this case, you can prove discrete holomorphicity, but somehow a stronger form of discrete holomorphicity that provides you exactly with the same rigidity theorem. So you get for free that it converges, meaning that you get it from the observable I described. The observable itself says, I'm converging because I decided to. Okay, yeah.
It's not really free, right? It's buy one, get one free.
Yes, exactly.
It's two for double.
But you really have to catch it. So you get for free, but the guy is here, you see, and you try to catch it, and it's very hard. The proof is very, very smart. Just for the conjecture, in this area, you get this SLE, and that's not the same. So it's where I'm telling that that's not the same critical phase. And there are two cases that are very famous. For self-avoiding walk, so I said here I will get SLE 8 third. That's what I said before. Here I get SLE 8. And that's the natural guess. You will say, so as I said, mu is not large enough in this case, or x is too large, so I get space filling. That's exactly SLE 8. For n equal 1, SLE 3 when you look at the critical Ising model.
So no matter what your penalty is, as long as it's small enough to get SLE 8,
Yes,
doesn't change?
that's a very funny thing, yes. But you will understand it in the second example. For or I will not manage to explain, but for O1, you get SLE 3, which corresponds to the critical Ising model. If you get above it, so you look high temperature expansion in supercritical phase, what you get is percolation. And somehow it's natural because the connection is not strong enough, so at the scaling limits you are just independent. And no matter which supercritical temperature you take, subcritical, sorry, temperature you take, it's okay. Supercritical.
Like the same relation you see in the random cluster model. If you take the
no, so in the random cluster model you don't see that because you really have a critical value where you have something non-trivial. Above it and below it, you get supercritical phase and subcritical phase. So that's trivial limits. You don't get an SLE there. So that's what is funny in these models. Okay, and so just to finish a few slides, what you cannot do is to work with the square lattice, because I know that I will get this question. So no. And the reason why is, please, I beg you, why is you can, okay, let's take even more latitude and we allow ourselves much more things, like to put fancy weights everywhere. And the thing is that there is only two families of solution where you can find a parafermionic observable, and one is trivial, or at least so it's not interesting us in the scaling. In our work. And the second one is the hexagonal ON model, which is included. So it's not necessarily easy to see that you can create the hexagonal ON model through this. But if you put the right weights, you will get exactly the hexagonal model. So we fall back on the one we were working with. And these points where you can find parafermionic observable, they are the same where in physics you can find what we call the Young-Baxter equality. And this is something very, very, very strong in physics. basically physicists know how to handle a model only if they know that, this equality. I guess I will finish here. Thank you. Yes.
Yes, but if you want to compute the connectivity constant in a similar lattice in 3D, you didn't use anything.
Yes, but somehow the reason why there is this square root of 2 plus square root of 2 is deeply related to the exact, what we call exact integrability of the model, and this is very typical from two-dimensional lattices.
If you find can you some lattice which has a
No, I don't think so. I think it's really too much related to this Young-Baxter equality and things like this. So you never know, but this kind of miracle somehow they hold in 2 dimensions.
The miracle is that 5/8 cancels, gives you...
No, that's not the real miracle. I mean, the miracle that was that Nienhuis, he takes this model and he modifies it for another model, and he modifies it again and for another model, and finally he can describe this model. But all this bijection between models, that's really something you know in 2 dimensions. There is a very, very deep literature and on exactly solvable model, and so all the work by Baxter and everything.
Is there an analog for the winding number in 3D?
So even the interface, notion of interface is not obvious in 3D. And I don't know, I mean, usually my bet will be that if you have an exact value for a model, is that there is self-duality somewhere. And that's the case for random cluster models. If you find a nice value take percolation, if it's 1/2 for the triangular lattice, it's because you have a self-duality property. And I will bet that in most cases, that's the reason why. Perhaps it's very, very well hidden, but that's the idea. So here, and self-duality is typically something 2-dimensional.
I think we'll thank the speaker again.